All right, so we're getting towards the tail end. We have 3 more sections to cover. Okay, it's ticking down. And these last 3 sections, we're going to come back to one of our, go ahead, Braden, one of our definitions of integrals. We said integrals can represent an antiderivative, aka working backwards. An integral can also represent the amount of change in a function, okay, from like a beginning point to an ending point. And we also mentioned how an integral can represent the area under a curve. So we're going to come back to that area definition in this section, and then in the last 2 sections we're going to relate the area under the curve to help us figure out volume of 3-dimensional irregularly shaped objects, which I think is kind of cool. So we have 3 more sections to cover, and we're going to be dealing a lot with area and then also volume, okay, kind of as a precursor. So we're going to use our colored pencils or writing utensils to make sense of this area under the curve, because we're going to step it up a bit. Instead of finding the area underneath one curve, we're going to try to find the area trapped between multiple curves, and how we can utilize calculus to help us figure out that trapped area. So we're going to go ahead and graph the f of x function, and we're going to find the value from negative 5 to 0 of the integral. So that means area under the curve. We're going to use one of your colors, I don't care which one you pick, to represent and shade that area. So let's first of all graph this function. We know it should be a parabola, we know it should be upside down, but we don't really know exactly where it might be located. Let's go ahead and try to graph it without a calculator. We'll use a calculator eventually, but how can you graph a function by hand? Can we figure out where some points are? How can we do that?
Plug in x value.
Pick x values. So what's an easy x value to plug in? 0. If we plug in 0 for all those x's, we get 4. Pick another x value. 1. Okay, so if we plug in 1, we'd have negative a half minus 2, which is negative 2.5, and then plus 4. So that's 1.5. We plug in 1, we get out 1.5. Let's pick some other ones. Maybe we'll go negatively, because notice how just between those 2 points, notice how the graph would be decreasing. So we're kind of on the right-hand side of the upside-down parabola. Let's go a little bit further to the left. If we try negative 2. Negative 2 squared would be 4. Negative a half of that would be negative 2. This would change to a plus 4. If we were to plug in negative 2 for x. So we have negative 2 plus 4, which is 2, plus another 4 would be 6. So we plug in negative 2, we get out 6. Let's try negative 4. Negative 4 squared is 16, negative a half of that's negative 8. Plug in negative 4 there, this would change to a positive 8, so those are going to cancel, and then plus 4 on the end. So we plug in negative 4, we get out 4. Alright, it looks like we have a general shape of the upside down parabola to help us out, so maybe we'll go ahead and just connect those dots. Alright, so there's our upside down parabola. Let's go ahead and choose one of our colors. We're going to shade in the area that represents this integral from negative 5 to 0. Okay, it's always to the x-axis. We'll eventually talk about area to the y-axis towards the end of this section, but for now it's just to the x-axis. And we also need to find the value. Okay, so actually calculate the area under the curve. We will do this by hand to a point, and then we'll go ahead and use our calculator to kind of finish it out for us. So let's go ahead and find the area under the curve. So our function was negative 1/2 x squared minus 2x plus 4. Let's go ahead and utilize another definition of an integral, aka antiderivative. Can we go ahead and work backwards from that function? We'll do our reverse power rule for each term. So if we add 1 to the power, the first term would be next to the third. Divide the coefficient by 3. We'll have a negative 1/6. The next term would be an x squared. The last one would be a 4x. Do we need a plus c?
No.
No. Why? Good.
Know the interval.
We know the interval, right, the bounds. Okay, so we'll throw in the bracket with the bounds. So which bound do we plug in first? 0, the top bound. Yep. All right, so plug in 0 for all those x's. We're going to get 0. And then according to the first fundamental theorem of calculus, it's top minus bottom. So we're going to go ahead and plug in negative 5. This is when I'll let you use your calculator. Okay, so go ahead and plug in negative 5 for all those x's and see what we get. What did we get if we plugged in negative 5? Did we find it?
The negative 24.
Uh-huh.
167.
0.167, there we go. All right, so top bound was 0, bottom bound negative 24.167. We are subtracting that bottom bound, so notice how it would change to a positive value. I hope that makes sense, because isn't the area above the curve, or not, above the x-axis? My bad. So there's the area of the green, well, my green section, yours might be a different color, but we found the area of that particular region, all right? Let's go ahead and check out another one. Graph the function 1/2 x plus 4. This one should be a little simpler for us because this is a line. So we'll go ahead and plot the y-intercept first, and we'll use the slope to help us get some other points. We're going to go ahead and shade the area for this region. We're still going from negative 5 to 0. So underneath that curve, maybe I'll shade it red. All right, so let's go ahead and figure out the area that we just shaded. So this is the g of x function. We'll have 1/2 x plus 4. Let's go ahead and work backwards, okay, antiderivative. So add 1 to the power, divide coefficient by the new power, and then we'll have a 4x on the end. All right, first fundamental theorem, top minus bottom. We plug in 0, we get 0, minus, go ahead, use your calculator, plug in negative 5. Bless you. How about negative 13.75? So if we're subtracting that, it would change to a positive. So there's the area of my red section. Okay, so we already know up to this point how to find the area under one curve. Okay, we did the parabola first and then the line second. But this can, bless you, this can bring us to a different point or something else to analyze. What do you suppose we would have to do to find the area of the region trapped between those two graphs? So I don't know what your color is, but if you look at mine, the trapped area would be just the current green section that's shaded in there. So we're looking at this kind of weird piece. What do you think we would have to do to figure out just that area? Can you visualize it? Go ahead, Stevie.
Subtract the 2.
Subtract the 2. All right, so we'll go ahead and subtract the area. We'll subtract the area found from the original functions. All right, so our first area was 24.167. The smaller area was 13.75. So our trapped area
Hey, Steve, you need to go clear some out.
yeah.
Can I go say something to GB real quick?
To who?
Can I go say something to GB real quick? He's talking trash on me. I can hear it.
Real quick.
I'd like to.
But you have to say it loud enough so we can hear it.
On the bowling ball.
You're going down, bro.
She's terrified.
Hey.
We're good?
Yep.
We got it cleared?
What?
We got it all cleared up? We're good? Okay. Are you playing him next?
No, we'll play the next round.
Then,
This one.
gotcha. Okay. All right, so let's take a look at this. We now know how to find the area trapped between two curves. We can simply find the individual areas and then subtract them together. But instead of doing kind of that long, tedious process, doing one area first, the other one second, and then subtracting them, if you're comfortable with that, more power to you. You can do that every single time. But there might be a shortcut. Let's see what we can do here. Let's go ahead and investigate this integral. So it's still -5 to 0 like before. We're still using the same f of x and g of x function. Let's see what happens. Okay, if we were to replace f of x with its actual equation, we can go ahead and write that down. And according to that integral, it's telling us to subtract the g of x equation. But you got to be careful. Notice how the g of x equation has multiple terms in it. So if you're subtracting that entire equation, you're subtracting every single term. So we have to have a 1/2 or minus a 1/2 x minus a 4. That minus sign kind of gets distributed in. Okay, be careful with that. Can we clean up that integral? Because right now we have 5 terms in there. Let's see, we'll have -1/2 x squared. We can combine the x's together. -2 minus a half is -2.5, but we can write that as a fraction. 5/2. And the 4's conveniently cancel each other out. All right, let's go ahead and work backwards. Okay, antiderivative. We'll add 1 to the power. We'll get x to the 3rd. Divide the coefficient by the new power, bless you, -1/6. The next one, we'll add 1 to the power, so that's x squared. Divide the coefficient by the new power, we'll have 5/4. And our bounds are -5 to 0. First fundamental theorem, top minus bottom. We plug in 0, no big deal. everything's going to be 0. Subtract what we get when we plug in -5. Go ahead, use your calculator. You get -10.417, and if we're subtracting that, it would change to a positive. What do you notice about this number?
Same.
It's the same area, okay? So it's the same area as previously calculated, okay? So notice how instead of having to solve 2 individual integrals and then subtracting their values, we can simply solve 1 integral to get our final answer. I'm not saying one way is better than the other. I'm not saying one way is quicker than the other. I'm just giving you options. Okay, so let's go ahead and make note of this, just in case you like this method better. We could individually calculate the area underneath the F graph, okay, which was kind of that higher parabola graph, and subtract that from the area under the g of x graph, which was the shallower line graph. So we could find the areas individually and subtract, but we found that that's exactly the same as simply doing 1 integral of f of x minus g of x. I hope this makes sense because this was actually one of the properties of integrals that we discussed way back when we first started looking at them. Okay, if you're subtracting 2 things together in an integral, you can break it up into their individual functions. Okay, I hope we can visualize that. So from now on, I don't care how you calculate the area. You can do one function and then the other and subtract. Or maybe you prefer doing just one integral to help you out. Right now, do we have a preference? Do you think one way is quicker than the other? Would you rather work with 2 integrals or 1? 1? I tend to agree, okay, but that's just me. So we're going to go ahead and practice finding the area trapped between 2 curves. So take a look at the one down below. Kind of an irregularly shaped interval where it looks like we're going from 0 to 2. We have one function that looks like a wave. So that's probably the trig function. Maybe we'll label that as sine of pi x. And then the lower function is probably x to the third minus 4x. Okay. If you're not sure which one is which, you can always kind of test a point. For instance, this is an x value of 1. If you were to plug in 1 in for x, sine of pi is 0. So notice how that's on the x-axis. If you plug in 1 for x into the other equation, you'll get -3. So that's down here. Okay, you can always test a point so you can clarify which one's which. So let's see if we can figure out this area trapped between the 2 curves. Can we first figure out the bounds? Where the trapped area begins and where the trapped area ends? 0 to 2. Okay. All right. The second thing we have to figure out, because if you notice the single integral that you guys said you wanted to use was f of x minus g of x. Order matters when you subtract. So we have to figure out which one represents the first function we should use and which one represents the second. Okay, so we have to be clear on which one goes where. I'm going to flip the page for a second. Okay. When we calculated the area in the previous example, we did the quadratic function minus the linear function. How is the quadratic and the linear related together on this interval? can you describe where the quadratic is located compared to the linear? Yeah.
Above.
It's above. So if we did quadratic minus linear for this example, the quadratic is the top function or the above function, and the linear was the below function or the bottom one. Okay? So we're going to have to figure out what's the top function on the area and what's the bottom function on the area. Let's relate it back to this one. Our top function we labeled was sine of pi x. And that means we would have to subtract the bottom function. This is very similar to that first fundamental theorem. Remember how we do top minus bottom for the bounds? It's kind of the same concept. We do top function minus bottom function to help us figure out that trapped area. Okay, very similar concept. We got to be careful though. Notice how the bottom function has more than one term in it. So if you're subtracting that, you have to switch all the signs. So it actually changed to a negative x to the third plus 4x. All right. From here, I want you to do calculator work. Can we type it in? What do we get? 4, good. There's the area of that trapped region. Okay. Now, in order to help you figure out perhaps what's the top function, what's the bottom function, remember when we did like the left endpoint, right endpoint, midpoint, rectangles, trapezoids, all those different shapes? You might find it visually helpful if you were to draw in like a line or a rectangle in that region. Notice how the top function here touches the top of the rectangle, and then this bottom function touches the bottom piece of the rectangle. The moment we start to measure area to the y-axis, we're going to start drawing our rectangles horizontally to help us out. So it's just some type of visual if you want to utilize that or not, but sometimes for me, I like to see it. So if we're having the area measured from 0 to 2 on the x-axis, we'll go ahead and draw in kind of that vertical rectangle to help us determine top function and bottom function. I know that might seem kind of common sense, but the moment we switch it to the y-axis, it might become helpful for us to draw in those rectangles. Let's try another one. I think we're on a roll. All right, picture to the right is the graph of f of x, kind of crazy looking equation. That's the curvy graph. And line L, which is tangent, aka only touching once, at the point 0, 3. So somewhere right there. Our first thing we want to do is find the region of R. Okay, the area of region R. We first should probably figure out the bounds on region R. So where does that area begin on the x-axis, and where does that area end on the x-axis? Do we know either one of those? Go, Dan?
Well, 0 is one of them.
All right, so the area is ending at the x value of 0, but we don't really know where it's beginning. Notice how the beginning point, though, is the x-intercept of that curve. So we're going to go ahead and utilize our graphing calculator to help us figure out that x-intercept. We're going to go ahead and graph the function x to the third divided by 4 minus x squared divided by 3 minus x divided by 2 plus 3 cosine x. Make sure you're in radian mode because we're dealing with trig. Before we hit graph, maybe we'll change our window to the window on the paper so it matches what we see. Looks pretty good. How might we be able to figure out that x-intercept? Are you familiar with the buttons to press on your calculator to figure out that point? We could go about it two different ways. That's why I'm wondering what we're more familiar with or comfortable with. Okay, second trace and 0. Okay, an x-intercept, aka or root, aka a 0, they all mean the same thing. So if you select that option, it's going to ask you a few questions. We're going to move our cursor to where we think the x-intercept is. And the first question it's asking us is to pick a point on the left. You see how it says left bound? So we'll hit the left arrow a few times. Then it wants us to pick a point to the right of where we think it is. You should see those arrows pop up. That's just your way of telling the calculator the x-intercept is somewhere in between those arrows. And the last question, it wants you to take a guess. So the exact 0 is negative 1.373. Okay, so that would be our bottom bound, negative 1.373. All right, so let's think about this region R. If you were to draw in some rectangles, okay, just as a visual, what function is at the top of those rectangles? It's the f of x, the whole thing. Like this whole equation is the f of x graph, the one we typed into our calculator. So we'd have x to the third over 4 minus x squared over 3 minus x over 2 plus 3 cosine of x. Okay. Since the rectangles are touching the x-axis, we do not have another function to subtract, because our area is going to the x-axis like it typically does. So we'll just go ahead and end it there. This is not a top function minus bottom function example, because the bottom function is simply the x-axis where the area ends. So I want you to do some calculator work. We'll go ahead and find the area of region R. Did we get it? Should be positive. Region R is above the x-axis. 2.903. Sound good, guys? All right. Perfect. Let's try the next question. Find the equation of line L if it is tangent to the graph. How do you find the equation of a tangent line? Point and a slope. All right. And we want to find it at the point 0, 3. So we already know what the point is. That's nice. Now we got to figure out the slope, which comes from the derivative. So let's go ahead and take the derivative of our function. We would have 3/4 x squared for the first one, minus 2/3 x minus 1/2, and derivative of cosine is negative sine, so we'd have to switch that sign. Or switch the addition sign, I guess I'll be specific. Alright, so let's go ahead and plug in 0 for all those x's. We could probably do this in our heads. The first x goes away, the second x goes away. Sine of 0 is 0, so we're only left with negative 1/2. Let's go ahead and write our equation. Y minus 3 equals negative 1/2 times x minus 0. So far, so good? Equation of tangent line, we've been doing that all year. Let's check out this line L a little bit further. At what ordered pair, other than the 2, 3, does the line L intersect the graph of F? So at the top, we're looking for this point here. Okay, since we have a calculator, we'll use that to our advantage to find the intersection. But you can only type in y equals equations on your calculator. So right now, the equation of the tangent line we wrote doesn't look like y equals mx plus b. We're going to have to kind of rewrite it. If we were to distribute in the negative 1/2 and then add over the 3, we would get negative 1/2 x plus 3. Okay, so this is your line L. Let's go ahead and type that in. How do we find the intersection on a calculator? Do we know what buttons to press? Second, trace again. Okay, so the same menu where we used the 0 function option before, but notice how option 5 says intersect. So we'll go ahead and choose that one. And we're going to move the cursor to where we think the intersection is. And we'll hit enter 3 times. 1, 2, 3. Once that word intersection pops up, you know that's the exact ordered pair. So we'll go ahead and copy down that answer. We have 3.3899, comma 1.3051. All right. Last but not least, find the area of S. So in the picture, S is that other shaded region. If we were to draw in some of those rectangles, just as a visual, notice how these rectangles have a top function they touch and a bottom function. So that we're essentially trying to find the area between two curves, which is going to involve some type of subtraction. So let's go ahead and see if we can fill in this integral. What are the bounds for that region S? Where does the trapped region begin on the x-axis? Where does it end on the x-axis? Can we figure it out? Let's see, this first point where region S begins has an x value of 0. And the second point that we just found, okay, aka the intersection point, has an x value of 3.3899. So that must be our beginning and ending bounds. So now we got to figure out the top function and then subtract the bottom function. If you look at the rectangles, if you draw them in, the top function is the line, which was the minus 1/2 x plus 3. And the bottom function is that f of x curve. So we have to subtract every single term from that f of x equation. So we'll have minus x to the third over 4 plus x squared over 3 plus x over 2 minus 3 cosine of x. You're subtracting the whole thing, which means all of the signs change. From there, it'll be calculator work. It's a lot to type in, but it's something we can do. Anybody get it? $6.982. Thumbs up? Good to go? I like it. Alright. We'll stop there for today. We'll try a few more tomorrow, okay? We're going to get used to identifying the top function and the bottom function on this trapped area, and then we'll utilize an integral to help us find that area.